Hi, my name is Reto Meyer and I'm the tech lead for Google's Android Developer Relations team. This is the first in a series of DevBytes created to help you improve the battery efficiency of your apps by changing the way you handle your data transfers. The mobile cell radio is one of the biggest sources of battery drain on modern smartphones, so making sure transfers use it efficiently can make a dramatic difference to your app's impact on the battery life. Now on the surface, this seems like a pretty simple challenge. If the cell radio drains the battery, just transfer as little data as possible, as infrequently as possible. Now that's a good start, but we want to balance that with providing a great user experience, one where the data your users need is available as soon as they need it, without them ever needing to hit refresh. Now that requires understanding how to optimize the timing of your data transfers, and that means understanding the cell state machine. Now in order to conserve power, the cell radio isn't kept on permanently. In fact, it goes through a series of state transitions in order to compromise between low latency data transfers and minimizing the impact on battery life. It begins over here, on standby mode, where it's drawing minimal power until an app initiates a data transfer. At this point, it transitions to full power mode, a process that takes around 2 seconds before performing the transfer. Now rather than dropping back to standby immediately after the transfer is completed, the radio will remain in full power mode for a set tail time, just in case further transfers are initiated within that window. This happens because dropping to a low power state reintroduces this power up latency. Not only that, but transitioning between states in and of itself is a significant power drain. Now if nothing happens during the 5 to 10 second tail time, the radio drops to this intermediate low power state that uses less battery than full power but has a lower startup latency than standby. If a new transfer is initiated, it will be promoted back to full power mode, and if nothing happens for another 30 seconds to a minute, it'll drop back to standby. The exact latencies and tail times vary between carriers, or even within carriers depending on where they are, as carriers try to balance low latency with longer battery life based on things like cell congestion and typical or prevailing network conditions. To understand how this might affect your app design choices, you start with this simple equation, then take the square root of the sum of the latency and idle times between each state, and then throw all of that out. Because it really doesn't require any maths to do, and it doesn't even matter what the specific latency or tail times are for any users of your app. The solution comes down to what I like to call the cookie droid conundrum. When scheduling downloads, do you transfer as much as you can as infrequently as possible, minimizing the number of transfers at the expense of bandwidth, or do you take the opposite approach, transferring as little as possible, performing transfers more frequently? Well, on the surface, the little cookie model appears sound. Less data transferred means less bandwidth, and less time spent with the radio active to transfer our data. And because we're downloading what we need on demand, we never download and process more than we need. Unfortunately, this results in a heavily fragmented use of the cell radio. From our knowledge of the cell radio state machine, we know that every time we perform a data transfer, the radio stays active for at least 5 seconds of tail time at full power, followed by anywhere from 10 to 60 seconds at lower power, before it finally returns to standby. That means every time you initiate a transfer, you're powering the cell radio up for at least 20 seconds. Now if we look at this more closely, you can see how an app like this one, whose radio use is indicated here, can drain the battery without transferring very much data. Each of these small peaks represents something like analytics data being sent back to the server every 15 seconds, while the larger peaks, they represent intermittent transfers based on user interaction, maybe clicking on a news article or looking at a restaurant listing. Now beneath that, we can see how this affects the radio state machine, with blue showing active transfer times, the red indicating the radio remaining in full power mode, yellow showing lower power mode, and the gaps between showing us where the radio is idle. Now we can see straight away that there are no gaps, meaning that while this app is running, it's keeping the cell radio powered on continuously. In fact, the regular updates alone are enough to prevent the radio from ever returning to an idle state. That shows us that the big cookie model is a far better approach to coordinating our data transfers. In this example, I've bundled all of the repeating transfers together, and the intermittent transfers have been largely replaced with aggressive prefetching. Now obviously you usually can't entirely predict what data users might need, nor can you ignore either client or server-side changes that need to be synchronized, but you can aim to minimize the number of radio state transitions through a combination of aggressive prefetching, in addition to batching and queuing any transfers that aren't time-critical and bundling these with user-initiated time-critical transfers or those initiated from the server. The result is a significant improvement in the amount of battery drain your app is responsible for. In comparison to the previous on-demand approach, the radio is now idle nearly 2/3 of the time. Even the active radio percentage has dropped significantly thanks to an improved download efficiency as a result of transmitting more data in each shot. So, taking the cell radio into account, you can minimize the battery impact associated with your app's data transfers by transferring as little data as possible as infrequently as possible. Defragment your network access by prefetching, batching, and bundling your transfers, and eliminate client-initiated updates and polling as much as possible. The most important thing to remember is that every time you transfer data, no matter how small, the radio is powered up for nearly half a minute. So every decision you make should be based on minimizing the number of times that this happens. I dive into each of these topics in more detail in other videos in the Efficient Data Transfer series of DevBytes, including looking at ways you can analyze your own data transfer profile and how to implement some of these best practices using simple code patterns, as well as implementing sync adapters and Google Cloud messaging solutions.